In this video, we're going to learn about what impedance is. So impedance is a way to generalize the idea of resistance into the complex number domain. So when we were dealing with regular systems, we had resistance, inductance, capacitance, and they behaved differently, and you had problems with them. For example, when you had a capacitor or an inductor, you had to use differential equations, derivatives, in order to work things out. And that was a bit of a pain. But it turns out if we turn things into the complex numbers, into phasors, we'll be able to treat resistance, inductance, capacitance as all one thing called impedance, and they will behave the same algebra rules as anything else. Now, how does this work? Well, first off, we're going to assume that our input voltage is going to be something in the form of a cosine. And, A cosine omega t plus phi. Now, if it's a sine, you can always use trig identities, turn it into a cosine. If it's a sine plus a cosine, again, there are trig identities you can use to convert it into just a cosine. If it's something else, there are other techniques out there that can convert it down to cosine. So for us, we're just going to stick with cosine, make our lives easier. So in that case, we have our phasor voltage, A angle phi. Now, when we want to look at our current, it's going to depend on what type of thing you have. So for example, for a resistor, we know just by regular Ohm's law, I of t is going to be V of t over R, which in this case would just be then A over R cosine omega t plus phi, which in terms of a phasor then would be A over R angle phi. And if you do your phasor voltage divided by your phasor current, you're going to have A angle phi divided by A over R angle phi. It's going to simplify down to just R. So this just tells us that the phasor impedance for a resistor is actually just equal to the resistance itself. On the other hand, for an inductor, we know that the voltage is L times the derivative of the current here. So when you do that here, you're going to have phasor voltage is L, and then if your current is, e to the j omega t, like we've seen before, the derivative of that is just going to be j omega, e to the j omega t, which is, phasor I here. So what you end up getting then is your phasor impedance, which is always phasor voltage divided by phasor current, is just going to be j omega L. So that is the impedance of an inductor, j omega L. You can do the same thing for a capacitor. The only difference is kind of reversed. Current is C times the derivative of the voltage. So you end up getting phasor I is j omega c phasor V, which means when you divide them, you get 1 over j omega c, and then sometimes we prefer to rewrite this as negative j over omega c, which you can get that by just multiplying top and bottom by negative j, and using the fact that negative j times j is just 1 in the denominator. So the main thing here you want to get out of this is that these are the three rules you will use to convert resistors, capacitors, and inductors into their phasor versions. Now, once you have them in their phasor versions, in the impedance, then everything works the same as if it was a resistor. You can combine two things that are in series, so let's call them, say, Z1 and Z2. You can combine them together to make Z1 plus Z2, and that's perfectly fine, just like if they were series resistors. One little comment, I'm using a box there because it could be a resistor, it could be an inductor, it could be a capacitor. So when we want to indicate something that might be any of multiple different options, we use a box. Since we can't use, for example, the inductor notation, we don't know if they're actually inductors. On the other hand, if you have two of these impedances that are in parallel, say Z1 and Z2, you again can combine them together using the parallel rule for resistors, Z1 times Z2 over Z1 plus Z2. So all your series rules for resistors work, all your parallel rules for resistors work. In fact, Y delta also works for impedances. But imagine when you have a bunch of complex numbers, doing Y delta is going to be even more annoying and long to do. So we usually try to avoid that if at all possible. Now, one thing that you're going to see up in the cases here, if you have a resistor, notice how there's no J there. You can write this as R plus 0J. That means the imaginary part is 0. There is no imaginary part. For an inductor, it's 0 plus J omega L. Since omega is your frequency, it's going to be positive. L is the inductance, it's going to be positive. That means it has a positive imaginary part. And similarly, for capacitors, it's going to be a negative imaginary part. So what we're going to do is if we combine a bunch of things together, if at the end of the result it has no imaginary part, it all cancels out, we're going to call that circuit resistive. On the other hand, if you combine it all together and it has an imaginary part that's positive, we're going to call that an inductive circuit. And lastly, if the imaginary part is negative, we're going to call that a capacitive circuit. So it's just a name to describe what's happening overall in a circuit. So if you have a resistor, a capacitor, and an inductor, but the capacitor is essentially having more effect on the circuit, you're going to end up having a negative overall imaginary part on your impedance, and that circuit would be capacitive. Even though there's an inductor there, it's just not as strong in some sense as the capacitor for the given frequency. Now for the last thing here is we're going to take a look at the standard RLC series circuit, and we're going to go ahead and combine those to find an equivalent impedance. The only thing is I'm not giving you what the frequency is for this, so we're not going to be able to get a specific number for our answer. However, we can still do the same process. So the first thing first, we're going to convert everything to an impedance. The impedance for a resistor is just R. Then we have a capacitor. The impedance for a capacitor is negative J over omega C. And then we have an inductor. And the impedance for inductor is J omega L. Now since they are all in series, to find the equivalent impedance, we can just add them together. And we can just rewrite this here. My equivalent impedance is R plus, for my imaginary part, it's going to be omega L minus 1 over omega C. So that right there gives you a formula that will tell you what the impedance is for a standard RLC series circuit if you know the values of R, L, C, and omega. As a little side note here, there is an important frequency for this circuit, and that's when your imaginary part works out to be 0. I'm not going to get into it that much in this video here, but that is going to be an important frequency. And you can actually just solve for it. It's not too bad here. You're going to get 1 over the square root of LC. And so this is going to be the frequency that allows you to turn your overall circuit into resistive. The imaginary parts cancel each other out. And this is what you're going to have.